Let's crack open whodunit. In whodunit, our job is to take a clue, a bitmap image, and create a verdict, another bitmap image that will reveal the hidden message or hidden image within that bitmap. So how do we do this? Well, first, after we open the clue file, then we want to update the headers info for the verdict file, the out file. We want to read into the clue scanline pixel by pixel and change that pixel's color as necessary in order for us to reveal the hidden clue. Don't worry, more on this later. And then finally, we want to write the verdict scanline pixel by pixel. Now, this may seem like a lot to do, but don't worry, you don't need to start from scratch. If we open the distribution code, take a look at copy.c. Copy.c does a lot of the things that we need to do for whodunit. It opens an in file and creates an out file, updating the header info for that out file. Then it reads into the scan line for the in file pixel by pixel, and each pixel it writes into the output file scan line, creating an identical copy of a bitmap. So it's not exactly what we need, but it's a great framework to start with. So let's start by copying copy.c into our whodunit.c file, making sure that we understand what each line does. The first thing that we have to do is to open the in file and open and create the out file. Copy.c does this using file IO, creating a file pointer for either reading for the in file or writing for the out file. The next thing to do is to update the headers info for the out file. Bitmaps are simply an arrangement of bytes. It's just a matter of how we interpret this arrangement. Take a peek inside bmp.h for a little bit more information. A bitmap is comprised of an info header, a file header, and then the actual pixels and padding. More on padding in a second, but let's just look at the variables within the bitmap info header. So bi bitmap info width contains the width of the image in pixels, not including padding. Then the height contains the height of the image in pixels, and bi size image contains the total size of the image in bytes, including the pixels and the padding. Now let's go to the bitmap file header, where bf size contains the total size of the file in bytes, including the pixels, the padding, and the headers. So the bf size can be calculated by taking the bi size image plus the size of the bitmap file header and the size of the bitmap info header. So how do we read into a file? If you follow along in copy.c, then you'll come across the fread function, where fread takes in 4 parameters. The first is a pointer to a struct that will contain the bytes that you're reading. Second, the size of each element to read, then the number of elements to read, and finally, the file pointer that you're reading from. So taking from that in pointer, you're going to put those bytes into that first parameter data. Now that we've read into the file, let's talk about pixels. Pixels are represented by 3 bytes, where each byte represents the amount of blue, green, and red respectively in that pixel. So if I were to say have the maximum amount of blue in a pixel, then I would have FF in the blue section. And if it were a pure blue pixel, then I'd have 0 green and 0 red. If, say, I had the maximum amount for blue, green, and red, then I'd have a white pixel. Here's a simplified example of a bitmap where I'm representing the pixels by their hexadecimal pixel notation. Now, I know that I just told you that FFFFFF indicates a white pixel, but that wouldn't really show up nicely on this slide, so bear with me and let's pretend that these are white. So we have our white pixels and then we have our full red pixels, 0 blue, 0 green, and full red. Together with those, we can use them as blocks, let's say, to construct an image. For this image, if you squint a little, then you might see a smiley face. All right, so let's take this one step further, and let's talk about the RGB triple struct. This struct will represent our pixels. So if I were to say make a green pixel, then I'd declare my RGB triple called triple, and then access the parameters within. RGBT blue, I'll set that to 0. RGBT green, setting that to full green, and RGBT red set to 0. And there I have a green pixel. You can access and change the RGB triple colors just as you do for any other variable. For instance, this code here asks if a triple's blue component is full, and if so, prints "I'm feeling blue." Now, remember that even though a pixel might have the full amount of blue in it, it's not necessarily going to be a blue pixel because you still have a contribution from the red and from the green. So, in order to ensure that you have a blue pixel, you might execute the following, setting the triple's RGBT green and red values to 0. Let's go back to our smiley, except in this case it looks a lot more like the clue input that you'll get in whodunit. There's a lot of red and it's a bit harder to see. So let's talk about how we might modify the colors to make the image more clear. What if we removed the red from each pixel, going through each RGB triple and setting the red's value to 0? Well, then it would look something like this. Still a little bit hard to see, but we can see the smiley a little bit more clearly. Or we might try this, changing only pure red pixels to white. And here we have a much clearer image. No need to squint or lean back for this one. Now, these are just two options for how we might make the clue image a little bit more clear. It's certainly up to you to try other ways. You might want to do a combination of removing some red, perhaps boosting some blue. Up to you, as long as the hidden message becomes clear. So now that we've modified those pixels, let's now write those into the verdict outfile scanline. We do this with the fwrite function, where, again, similar to fread, takes in 4 parameters. The pointer to the struct that contains the bytes that we're writing, the size, the number, and then the out pointer, the file pointer that we're writing to. So again, check out copy.c and see if you can find the section that does this. Last but not least, we need to talk about padding. In a bitmap, each pixel is 3 bytes. But a requirement for the bitmap file format is that the length of each scanline must be a multiple of 4 bytes. So that means that if the number of pixels isn't a multiple of 4, then we need to add some padding. And this padding is just zeros. Say I have 4 RGB triples. Well, each triple is comprised of 3 bytes. So since I have 4 of them, 4 times 3 is 12, and 12 is a multiple of 4. So I don't need to add any padding in this case. Now instead, say in my scan line I had 5 RGB triples. Then 5 times 3 equals 15, so that's not a multiple of 4. In order to get to 16, the next multiple of 4, I need to add 1 byte of padding. Then if I have, say, 6 RGB triples, then the amount of padding that I have to add in order to get to a multiple of 4 bytes is 2. Lastly, in this example, if I have 3 RGB triples, then that's equivalent to 9 bytes. So to bump it up, I have to add 3 more bytes of padding. It's important that we have a firm grasp on the concept of padding, but we don't need to come up with the equation because it's provided for us at the bottom of the slide, in the specification, and in the distribution code. If we look at the formula, then we see that the 2 parameters are the BI width and the size of the RGB triple. Now, the size of an RGB triple is always going to be 3 bytes, so the only thing that will ever change is the BI width. Now, in this case, the clue and the verdict have the same width because all we're doing is changing the colors of the pixels, so the padding is going to be the same. Now, padding isn't an RGB triple, so we won't be freading or fwriting it. Instead, we use the fputc function, which takes in the character to write and the file pointer to write it to. So, in this case for padding, we'll be putting the zeros into our verdict outfile. The last thing that we need to talk about is the file position indicator. Whenever we're reading into a file, there's the file position indicator, basically like our cursor, that keeps track of where in the file we are. So if we ever want to move that cursor, then we use the fseek function, which takes the file pointer that we're seeking over, the number of bytes to move that cursor, and then whether we are moving relative to the current position of the file, the beginning of the file, or the end. So again, very useful to understand this function by going into copy.c, seeing where that function is called, and understanding why. All right, we're ready to solve the mystery. We've opened the in file, updated the header's info for the out file, read into the clue scan line pixel by pixel, changing those colors as necessary and writing them in to the verdict scan line. And with that, you've completed the problem. My name is Zamila, and this was whodunit.